Hello guys. Um, in this video, we are going to study the difference between continuous random variable and a discrete random variable using an example. So think about this example. Suppose that you are waiting for a bus and the arrival time is random. It is supposed to arrive at noon, say, but it may come early or come late. So it's random. Anyhow, um, and when we study a random variable in the previous chapters, the method we used was to list all the possible outcomes. Like the simplest case, like binary case, there are two outcomes, and when there are two binary variables, there are two by two cases, and in binomial distribution, still there are n plus one number of outcomes. So we could list all the possible outcomes and attach probability to each of them. That was the approach so far. But it is not possible anymore because the time, the arrival time, is a continuous random variable. That means there are uncountably many moments in any time window, right? Even if you choose, say, uh, even if you choose like any small time frame, still there is an infinite number of moments with between those two time moments. So it is impossible to list all the possible outcomes. This is the typical problem, common problem for any continuous random variables. So the our approach does not work here. We cannot list all the possible uh, outcomes. Like even if you say 12 o'clock, 12 and 1, 12 and 2, 12, 3, still there is many more, or like infinite number of moments in between or minute. So in that way, it is impossible to list the possible outcomes. Therefore, we are going to use a totally different approach. Think about this method. The bus is supposed to arrive at noon, say, but I know that it can come early or late by up to 10 minutes. So at most 10 minutes late or 10 minutes early. So and to simplify the probability model, I'm going to assign. So I'm going to assign 100% in between 11:50 to 11:10, 12:10. So it is supposed to come here, but actually it may arrive within 20 minutes, and that is 100%. So simply 100% lies on a 20-minute interval. Then additionally, I'm going to consider this, think about this. I will assume that the probability is proportional to the length of time interval. So it is 100% for the bus to arrive within 20 minutes, plus minus 10 minutes. Then what is the probability for it to arrive within plus minus 5 minutes? Then I'll say it's 50% because the time interval is half of the whole interval. So the probability is also proportional. Probability is also half of the whole interval. So it makes sense. It is restrictive. It's a just a simple example, but it makes sense. As a time interval becomes smaller, narrower, then the probability will be smaller. So it's hard to make the time within that interval, right? So then, just as a simple practice, what would be the probability that the bus arrives between plus minus 2 minutes? Remember, plus minus 10 minutes contained 100%, and probability is proportional to the interval, length of the interval. What is the answer? The answer is 20%. The answer is 20% because 100% was put on 20 minutes. So you may think each minute accounts for 5%. So it is 5% for each minute. So 4-minute window, a 4-minute interval will have 5 times 4%. So 20%. Or 4-minute interval is 1/5 of 20 minutes. So the probability is also 1/5. So either way, this is how we are going to measure the probability. We cannot list all the possible cases, but still you can measure the length. Any interval uh, has a length, but any interval has infinite number of outcomes. That was a problem. Any interval has infinite number of problems. Still, we can measure how wide the interval is. That is our approach. Then the next question is a little more tricky. Then, following the same approach, what is the probability that the bus arrives exactly on time? Exactly at noon. It was supposed to come at noon. Then, what is that probability? Think about this. And the answer to this question is 0%. 0%. The answer is 0. Because when I say exactly at noon, it means it's one moment. It's just one point in the timeline. So it has no length. A point has no length, and it is just one moment. Or you may think it this way. Like when I say exactly at noon, I do not allow any second error. Like 1 second late is not on time. 1 second early is not on time. And suppose you have a super accurate scientific stopwatch timer, then it does not allow you any microsecond error, which is impossible. A bus cannot make that like cannot arrive right on time at this much accuracy. Of course, in theory, we can be as accurate as we want, and we assume perfectly accurate situation. Anyhow, one point. The main idea is one point in line has no length. So a line, a line consists of infinite number of points. When you have a lot of dots, then and when you connect them, it is a line. But point has no length, but the line has a certain length. That's the difference. So the probability is 0. This is true. It's not a trick. It's mathematically true. In a continuous random variable, one point has no probability. So this is true for all continuous random variables. Like for example, a tall coffee cannot contain exactly 12 ounces. A tall coffee is supposed to contain 12 ounces, but you cannot make it uh, super accurate, like as accurate as like your measurement. And you cannot drive a car exactly at 60 miles per hour. When I say 60 miles per hour, it does not allow any error. 60.00001 is not 60 mile per hour. And the weight of a wild caught salmon cannot be. I, oh, excuse me. So there is a typo. Cannot be 1 pound. So, so instead of these approaches, we are going to define probability in these ways. What is the probability that a tall coffee has less than like 19 ons or like say 11 ons or any number? And what is the probability that you drive a car faster than 60 miles per hour? And what is the probability that a wild caught salmon is between 1 pound and 2 pounds? So you can define those probabilities. There is no problem in defining these, but these probabilities are simply 0. So you don't need to consider these probabilities. It's automatically 0, as like because the random variable is continuous. Therefore, as I said, it's mathematically true. If x is a continuous random variable, one point probability at a point is zero, simply zero. So equality, probability defined by an equality, has no meaning. It's meaningless. So we cannot define probabilities in this way. Instead, we are going to use inequality, probabilities defined by inequalities. But because one point has no probability, it makes inequalities easier because one point has no probability. Probability that a random variable smaller than equal to a value is the same probability as x is strictly smaller than the value. So the difference between these two, the left hand strict weak inequality and strict inequality, is that the difference is just one point, whether the inequality includes the value or not. But one point has no probability. So inclusion of the endpoint does not matter. Has no effect on the probability. So similarly, the other way, greater than or equal to or strictly greater than has the same probability. Again, the main idea is a one point has no probability. So strict inequalities and weak inequalities, uh, another typo, sorry, uh, do not matter when you define a probability. So so keep this in mind. One point has no probability, but we may use inequality. And then it brings us back to the cumulative distribution function. We used cumulative distribution function when we defined the median and the quantiles, and it's actually much more important than uh, what we learned at that chapter. So cumulative distribution function is defined as usually capital letter X, capital letter, and so when you input a lowercase x, this function returns the probability that a random variable is smaller than or equal to the value, the input value. This is a function which changes as the lowercase x changes, and this is how we define and characterize the probability. Mathematically, it's much more important in probability theory. Mathematically, the CDF characterizes the random variable. When I say characterizes, mathematically it means two things. First, all the random variables have one cumulative distribution function, and if two random variables have the same cumulative distribution functions, they are the same random variables, right? That's the mathematical definition of characterization. And if you know, and also it implies that if you know the CDF, of a random variable, then you can calculate any probability or anything uh, from the CDF. So it contains all the information of the random variable. It's mathematically very, very important, and we are going to use the cumulative distribution function as the starting point of a probability definition. Okay, in the next video, I'm going to use an example to uh, to study how we use cumulative distribution function. Okay, thank you for watching the video. See you in the next video.